Alrighty, good morning, guys and gals. Um, Sorry, excuse me. So today we're going to continue our kind of discussion of applications of the derivative. We have a few more kind of interesting things to look at. Today is an especially fun one. I've also been kind of paying attention to where you guys are in the homework and what's being asked for in office hours. So I think it would be wise to review some concepts also. Just to make sure we're all on the same page. Some things that I've been asked about a lot and I think are worth reminding or reinforcing. So I'm going to go ahead and turn on the screen share here. Fire up the document camera. It's not ready. Okay. All right. So of course, this is Calc 1, MAC2311, section 002. It's a lecture. And today is the 26th of February. 2 more days left in February. It's just moving by so fast. Let's see. I think the very first thing we should do, actually, is take a vote. So remember, we talked last time about whether the exam, so the exam to vote. You have 2 choices. Your first choice is exam 2 is done before break. One week from today. What's the actual date there? I think it might be the, first, no, it's 5th, yeah. 3/5/21. This means covering sections up through 4.5. So today would be the cutoff for those. Sorry, not today. Monday would be the cutoff for exam 2 then. So this would be sections 3.5, 3.6, 3.7, 3.9, 3.10. 3.5. 3.7 now. 3.9. 4.1. 4.3. 4.4, which we're going to talk about today, and 4.5, which we would be talking about on Monday. All right, so here's your first choice. The second choice is that exam 2 is done the day we come back. Or, let me see what we're actually looking at here. So let's see if we're going to be off all this week. Next week we would, yeah, so that means we would not be able to fart around. We would have to have the exam on the 15th. And there's good reasons for that. Let me show you another thing here. Namely, you guys really want to get your exams back before the drop date, and the drop date is the 24th. So if we were to fart around at all, we wouldn't be able to get that done in time. So exam 2 is done on the day we return from spring break. Which we said was 3:15, right? Yeah. covers all the same stuff, but one more section, 3.5, 3.6, 3.9, 3.10, 4.1, 4.3, 4.4, 4.5, and 4.7. And 4.7 is a tricky section. If we go with option 1 and we do the exam before break, then 4.7 is going to go on exam 3. If we do option 2 and we do the exam after we return from break, then we'll be having a test as soon as you get back from break. So there are downsides to both. 4.7 really does belong on exam 2 because it's an application of the derivative. But on the other hand, do you really want to have a test right after you come back from break? These are the main things to keep in mind. So I will go ahead and set up the poll. Okay. Make it anonymous. So if you elect to have the exam after the break, that's not always the end of the world, but it means that you need to study over break. Yeah, really, Holly, it's up to you guys. So personally, I know that even when we say we're going to study hard over break, it often doesn't really shake out that way. So I would be hesitant to have the exam the day after break. Now, it all depends on your personal level of responsibility and how comfortable you are, saying I am for sure going to do this thing. But it really is your choice. And I think it could go well either way, as long as you guys are aware of the decisions you're making and you plan accordingly. Doing the exam before break means technically less time to study, but that's also less time to forget. If you spend all of spring break drinking beer and going to the beach and doing whatever, then you're just going to forget like meaningful amounts of what we've learned. Conversely, if you are going to spend spring break actually studying and working hard, then having that extra time might be a really good way to prepare. But in my experience, people, when given that extra time, don't usually use it wisely. But it depends. It totally depends. It's one person's preference and responsibility level. So I'm going to go ahead and launch the poll. You just select the option you want. I want the exam before break. That would be 3/5, a week from today. I want the exam after break. That would be Monday, 3/15, literally the day we come back. Either one is okay with me. All right, there we go. I think I'm still waiting for one person to vote. But even if that one person voted for option 1, option 2 still wins. So it looks like we're going to have exam 2 after break. All right. Them's the breaks. I'll stop saying the word break. It's starting to lose all its meaning. So exam 2 is going to be on 3/15. It will be March 15th, the day we come back from spring break. This means you guys really need to spend spring break doing some mathematics. And here's my recommendation, and whether you follow it or not is up to you, but here's my recommendation. You're off from the 8th through the 14th, right? No school all these days. That's wonderful. take a few days to enjoy your break. 8th, 9th, 10th, whatever. The 12th, the 13th, the 14th need to be study days. Ideally, you would study a little bit every day. You would take the whole break seriously and spend a few hours each day, or at least 1 hour each day working on mathematics. But at the very least, the 12th, the 13th, and the 14th, every single one of those days, you need to spend at least 2 hours preparing. All right, that's my official advice, since this is the path you guys have chosen. Okay, that's that. Let's get back to what we need to talk about then. So this is what we're going with. So there were one or two things I wanted to kind of clarify, or not, I don't know, clarify, but make sure we're all really comfy with. And one of those things is the definition of a critical number. So to say C is a critical number for f of x means two things. First, C is in the domain of f, and f primed of C is 0, or f primed of C is undefined. And this first one people tend to forget. So when you're hunting for critical numbers for a function, if somebody asks you, hey, find me all the critical numbers of this function, the first thing you should really do is find the domain of the function. And you'll notice one or two of your problems in the homework have you do that. They say, find the domain of f, okay, find the critical numbers for f, or find the domain of f, find f primed. The reason for that is when you're hunting for critical numbers, those critical numbers, in order to be a critical number, they must be in the domain. So this is worth being mindful of. I just wanted to make sure you were comfy with that. The other thing I wanted to do is solve at least one related rates problem, because I know those are tough. So,
hey, I got a quick question.
Sorry. Yeah.
Are you going to be releasing the project and the study guide?
So the study guide, I will definitely release. Yeah, I don't see any harm in releasing it sooner rather than later. If we're going to have the exam the day we return from break, the normal rule is to release it a week before the exam. But I'll go ahead and put that out as soon as I can. If I have time to publish it today, I'll do that. Otherwise, I'll get it out sometime over the weekend. The project isn't on the syllabus, so I can't have like a graded project. But what I'm going to do is hunt around for like worksheets or materials that I used to give people in class, and I'll publish some of those for you guys who want extra practice or extra things to work with. So I should have like, yeah, some old labs, stuff like that, that I could give you guys to play with if you're looking for it. It occurred to me that it really wouldn't be fair for me to have a great project because it's not in the syllabus, but I'll publish something for you guys to work as extra study material. And I'll publish it as a project on Canvas as soon as I can. So the study guide I'll get out before Monday, and then the little project or whatever supplementary materials I'm able to find for you guys to study with, I'll publish those at the same time. They'll go up in Canvas. I'll make an announcement there.
Okay, cool. Appreciate it.
Of course. All right. So I wanted to look at least one other related rates problem. And let's see. So this one we did in class. This one we did in class.
Can we do the last one?
Let me see. Which one is the last one? I think this one we did. Oh no, this is the one with the angle. Okay, yeah, if that's the one we can do that one. This one.
That one was giving me trouble.
Sure. A 10-foot ladder resting on a wall. This is a lot like the setup we had in class. the base is going to start sliding away. But now, instead of finding the rate of change for the height, we want to find the rate of change, find how fast the angle between the ladder and the ground is changing. So it's kind of like the kite problem, if you guys remember the kite problem we did in class. All right. So more related rates practice. A 10-foot ladder is resting against a wall. And the bottom begins to slide out. We want to find how fast is the angle between the floor and the ladder changing when the ladder is 8 feet from the wall, when the base is 8 feet from the wall. There's something I forgot to put in here. Slide out at, what was the speed? 0.9 feet per second. Okay, here we go. This is me inserting the speed on the baseline. The setup here is like this, right? Here's your wall. Here's the floor. And you've got a ladder. There's the base of the ladder. There's the top of the ladder. You know that the base of the ladder is starting to slide out like this. The thing they want us to find is how this angle is changing. So I should label this angle. I'll call it theta. The other things that are changing in this picture, well, the length of the ladder doesn't change. That's always 10 feet. But this distance here is changing. So let me call that by some variable. Call it x. And this distance here is changing. So the top slides down as the base slides out. So I'll call this y. And everybody's comfortable with what's going on here, right? This thing slides that way. As that happens, this thing slides down. And in the past, we've solved the problem to find how fast the top is sliding down as this slides out. But now we're trying to find how fast is this angle changing as this base slides out. The base is sliding out at 0.9 feet per second. So let me ask you first a very qualitative question rather than a quantitative one. Is this angle theta increasing or decreasing as this guy slides out?
Decreasing.
Good, right? It's decreasing. It's becoming a more shallow angle. All right. Just want to make sure we're all following the picture here. Next, I'd like to kind of take stock of what I want and what I know. Can somebody tell me, in terms of derivatives, what it is that I'm after? What do I want?
Would it be the derivative of the tangent of theta?
That's getting a little bit far ahead of where we're looking for. So they asked me how fast, how fast is the angle between the floor and the ladder changing when the ladder is 8 feet from the wall, right? So just in terms of, we've got these three variables, y, x, and theta. One of their derivatives is the thing I want. Which one of their derivatives?
The d theta or dt?
Very good. I want d theta dt. I want the change in theta over the change in time, right? The rate of change of theta. I say, how fast is the angle changing? That's d theta dt. So I want d theta dt, specifically at the moment when the ladder is 8 feet. So I want d theta dt when x is equal to 8. All right, what do I know?
You know the speed. Or the, yeah.
In terms of derivatives, like which, the thing that I would put here that is kind of similar to this, I'm looking for derivative information that the problem gives me. Like, do I know something about dy dt? Do I know something about dx dt? Maybe I misheard you, Robert. But anybody who's comfy with this, go ahead and answer. Specifically this information. What is this?
dx dt.
Yeah, good, good, good. That tells me dx dt. The base of the ladder is sliding out at 0.9 feet per second. So x, this side length, is increasing at 0.9 feet per second. So dx dt is 0.9. All right. Now there were some suggestions, something to do with tangent. How can I get a relationship between theta, whose derivative I want, and x, whose derivative I know? I think that when we did this with the kite problem, what I did is I actually wrote down 3 different trig functions of theta just to kind of get a feel for them. Let's do that same thing here. I can write down the sine of theta, the cosine of theta, the tangent of theta. What are these in terms of my picture up here? Let's start with sine theta. If I'm looking at this triangle here, which is a right triangle, right, walls meet the floor at 90 degrees. What is the sine of theta?
y/10.
Good, right? It's the opposite over the hypotenuse. So this is y/10. What is the cosine of theta?
x/10.
Good. And the tangent of theta?
y/x.
Yeah. All right. Now I want to be lazy. Which one of these is easiest for me to work with and why?
Cosine, because we know d of x.
Perfect. Yeah. So I know dx dt. So this guy relates exactly the thing I want, theta, to the thing I know, x. If I were to use, I could use sine, I could use tangent, but they would both require a meaningful amount of extra work. Because in order to get this, this is a y, and I don't know dy dt. I'd have to solve that other related rates problem to find dy dt in order to make use of this. And tangent has the same sort of issue. I don't have any information about y. So if I was going to use either this or this, I would have to, at the very least, solve some expression for y and get it in terms of x in order to proceed. So this one is nice. This is nice because it relates the variable whose derivative I know to the variable whose derivative I want, and nothing else. All right. So I'm going to work with that. What do I mean when I say I'm going to work with that? I mean, I'm going to differentiate on both sides with respect to time. right? So I want d theta dt, I know dx dt, and the way to get those things to show up, starting with this, is to apply the operator d dt to both sides, because d dt says take the time derivative, and these are time derivatives. On the right-hand side, do I need the quotient rule?
Yes.
So it's true that I could use the quotient rule, but this is one of those places where we can learn to save a lot of time. The quotient rule applies to ratios of functions, right? This thing down here, though, this is actually a constant. So if we want to save ourselves some time, you can think of that like this, right? 1/10 times x is 1/10 times x over 1 is the same as x over 10. So this is going to be much easier than using the quotient rule because constant multiples pop out of derivatives. On the left-hand side here, I won't do anything in this step. I'll just leave it alone. And in the next step, I'll actually take my derivatives. So on the right-hand side, when I differentiate 1/10 times x with respect to the variable t, I just get 1/10 times dx dt. No product rule, no quotient rule necessary because constants just come along for the ride when we take derivatives. On the left-hand side, I need to use some chain rule. The derivative of cosine theta is negative sine theta. And then because I'm taking the derivative with respect to t, not with respect to theta, I need to multiply by the derivative of the inside. And that's good because that's what I want. That's d theta dt. This implicit differentiation step is I think one of the things that folks really struggle with on these problems. So I'd like to take a second and make sure we're really comfortable with where everything here came from. The problem could become messy at this stage if you try to invoke some quotient rule over here, or if you're not comfy with how to differentiate this implicitly with respect to t. So are there any questions about where these pieces are coming from? All right. Well, now we're in pretty good shape. I know that dx dt is 0.9. I know I want d theta dt when x is equal to 8. There aren't any x's in this equation, but there is this sine theta. So what I need to do, let's see. This is what I want. I know this, but I need to figure this out. At the moment, when x is equal to 8. So I'm differentiating with respect to the variable t here, right? And the variable that's inside here is theta. Theta is a function of time. Theta changes over time. So I'm applying the chain rule here. In the same way you would apply the chain rule if this was a ddx and this was cosine of y, you would get negative sine of y times dy dt, or negative sine y times y prime. I'm differentiating implicitly. It's because this variable here is different than the variable in here. Since the variable down here is different than the variable in here, I need to multiply by the derivative of the inside. It's what we called implicit differentiation. It's really just the chain rule. So the outer function is cosine the derivative of the outer is negative sine, and we leave the inside alone. And then by the chain rule, we have to multiply by the derivative of the inside. Well, the d dt derivative of theta is d theta dt. If this was d theta, then this would be d theta, which is 1, and you would just get negative sine theta. But because the variable down here is different than the variable in here, I get d theta dt. So this is, again, that implicit differentiation thing. So my advice, if you're struggling with this stuff in the related rates problems, is to go back a little bit in the homework to the implicit differentiation problems and make sure you're really comfy with the notation there. I would be happy to work some more of these in office hours with anybody who wants to see it. That might also be helpful. But yeah, that's where this is coming from. All right, we're just multiplying by the derivative of the inner. And because I'm taking my derivative with respect to t, the derivative of theta is d theta dt. Cool. All right, so this is the piece I don't know, right? This is the thing I'm trying to solve for. I know this. This is a constant. This is the piece I don't know. So I need to find this sumbitch. To find this guy, I'm going to redraw this picture when x is equal to 8, because again, I'm interested at the moment when x is equal to 8. So I'm going to label this as star. I'm going to redraw that picture. I'm not going to redraw the whole thing, just. All right, so this is 10, this is theta, and I'm interested at the moment when x is equal to 8. What I want is sine theta, right? It's negative sine theta. In order to get that, I need to find what y is. So I need sine theta. Sine theta is the opposite over the hypotenuse, right? SOHCAHTOA, opposite over hypotenuse, that's y over 10. So I just need to figure out what y is here. I know that by Pythagoras, 8 squared plus y squared is equal to 10 squared, right? A squared plus b squared equals c squared. So that's 64 plus y squared equals 100, which means y squared is 100 minus 64, which is 36. So y is 6 when x is equal to 8. And now I can take this information and update my equation star. All right, I've got this. Now, plugging everything into star, we get, let's see, so sine theta, if y is equal to 6, sine theta is going to be 6 over 10. So I'll first rewrite the equation here. Negative sine theta d theta dt equals 1/10 dx dt. If I'm going to plug all the good stuff in here, negative sine theta is negative 6 over 10. Don't worry about simplifying, we'll get there. D theta dt is the thing I'm trying to solve for. 1/10 is just 1/10, and dx dt is 0.9. I like to rewrite everything as fractions. 0.9 is 9 over 10. So this is negative 6/10 d theta dt equals 1/10 times 9/10. So on the left here, 6 over 10, that's the same as 3/5. So negative 3/5 d theta dt is equal to 9 over 100. And now I can kind of multiply by the reciprocal of -3/5. Solving for d theta dt, I get 9/100 times -5/3. And there's some cancellation here. I'll have -9 divided by 3 is 3, and 100 divided by 5 is 20. So -3/20. What are the units of d theta dt? What is theta measured in, and what is t measured in?
Wouldn't theta be measured in radians?
Yeah, theta is measured in radians. So this is radians per second. So d theta dt is shrinking, so it's -3/20 of a radian per second, or 3 radians every 20 seconds. Cool shit, right?
Where did the sign go, by the way?
Say that one more time, Ryan.
Where did the negative sign go from the second equation?
So plugging in sine theta. So that's what we were doing over here. I needed to find sine theta, right? Which is y/10 at the moment when x is equal to 8. So I redrew this triangle and I solved for y using Pythagoras here. I found that when x is equal to 8, y is equal to 6. So sine theta is y/10 is 6/10. So negative sine theta is -6/10. So it's coming from the triangle here that I had to solve.
Got it. Okay.
This is a pretty common thing. So the way a lot of these related rates problems go is you draw your picture, you label everything with variables, you differentiate the appropriate equation, and then you look around at what you have and you realize some of what you need will have been given to you already, but some of what you need will not have been given to you, and you have to redraw your picture and solve for that thing at that particular moment. That's a very common theme in related rates problems. One place you guys can look for these if you want more examples, and this is the last thing I'll say about this. This guy, Patrick JMT, he's awesome, and he's going to have lots and lots of stuff. So I'll just copy 1 or 2 of these into the chat here, and if you want to, you can take a look at them in your own time.
I was watching him for implicit differentiation, and we're only doing we're not doing the multiple implicit differentiation, are we?
I think there were 1 or 2 problems where you had to find y double prime using implicit differentiation.
Okay.
But it's not a main focus. It's not something I would likely put on a test, but you should be comfortable doing it. There's nothing too crazy about it. So there's a couple more Patrick JMT videos you guys can watch. He is really good. The way he explains things is very gentle, he uses language very carefully, and his notation is good. All right. So on to the lesson for today. Today we're talking about indeterminate forms and L'Hopital's rule. This is section 4.4. This is something that's going to be important for us, and then it'll be important again in Calc 2, very much so. I'm going to state the theorem real quick, but then I'm going to show you lots of ways to use it. Cool story behind L'Hopital's rule. L'Hopital was a guy, just a dude, a French dude, and he wasn't super great at math. He was pretty good, but he wasn't able to come up with his own shit very well, and he wanted to be a famous mathematician. So what he did is he hired Johann Bernoulli, who is a very talented mathematician, to come up with some shit for him. He paid the guy, and then he repackaged it, put his name on it, and published it. So we call it L'Hopital's rule, but it really should be called Johann Bernoulli's rule. what this says is, if the limit as x goes somewhere, say to c, of f of x over g of x looks like infinity over infinity, or 0 over 0, i.e. the lim as x goes to c of f of x is plus or minus infinity, and lim x goes to c g of x is 1 of plus or minus infinity, or lim x goes to c f of x is 0, and when x goes to c g of x is 0. If the top and the bottom are both going to infinity, or the top and the bottom are both going to 0, then you can try again after differentiating the top and the bottom. It's kind of a cheat code for tricky limits. You can only use this if the top and bottom are both going to infinity or both going to 0, but in those cases, it's totally fair game. It's not always appropriate to use. Oftentimes, those limits we can crunch out just with algebra, but sometimes it's the only way to get things done. The word here is indeterminate. Indeterminate forms and L'Hopital's rule. The proof of the theorem is not hard, but I don't want to burn time on that because it's also not insightful. So let me go ahead and just show you some examples. These, by the way, I should tell you, these two things here, infinity over infinity and 0 over 0, these are called indeterminate ratios, right? They are a type of indeterminate form. So an indeterminate form is an expression whose value can't be discerned from the expression. Infinity over infinity could be 1, it could be 5, it could be negative 12, it could be 0. It totally depends on kind of where the infinities are coming from. And 0 over 0, you've seen this a lot, right? All of those limits that defined a derivative first looked like 0 over 0. All of that h to 0 stuff that we did at the start of the term, if you just plugged in 0 there, the bottom would be 0 and the top would be 0. So these expressions are called indeterminate forms because just based on the symbols that are used to write them, infinity over infinity and 0 over 0, you can't tell what they are. These specific ones are called indeterminate ratios because they're fractions, which is a ratio. Ratio is another word for fraction, whose value you cannot tell right away. Indeterminate fraction, indeterminate ratios. L'Hopital's rule can only be used on indeterminate ratios. Before the end of the day, I'm going to show you several other indeterminate forms and how to handle them. You have to turn them into indeterminate ratios before applying L'Hopital's rule. So some examples. Let's take something like, how about then x goes to negative 1 and x squared minus 1 over x plus 1. All right. So if you just plug in negative 1, this looks like negative 1 squared minus 1 over negative 1 plus 1, which is 1 minus 1 over negative 1 plus 1, which is 0 over 0, which is an indeterminate ratio. Right, 0 over 0. I don't know what this is. This could be anything. We know one of the ways to handle this is to factor the top and cancel the common factor and then try again. But what we now have is a kind of slicker, easier path to get to this limit. And here's the notation I would like you guys to use. When you're using L'Hopital's rule, over the equal sign that connects the thing that you're working on to the next step where you're going to use L'Hopital's rule, just write a little LH or a little L, something to let me know that you're using L'Hopital's rule. We'll differentiate the top. The derivative of x squared minus 1 is 2x minus 0. We'll differentiate the bottom. The derivative of x plus 1 is 1 plus 0. And we'll try taking that limit again. This time, when I plug in -1, I get 2 times -1 over 1, which is just -2. And that is the correct limit. If we factor the top, we'll get x plus 1 times x minus 1. You can cancel the x plus 1s, you get x minus 1, and -1 minus 1 is -2. So this is a limit where we could have used we could have done this without L'Hopital's rule, using algebra. When x to -1, x squared minus 1 over x plus 1 is when x to -1, x minus 1 times x plus 1 over x plus 1, which is ln x to -1, x minus 1, which is also -2. All right, because you can cancel these x plus 1s downstairs and upstairs here. That bottom is like x plus 1 times 1. But there are many limits where we cannot do this sort of thing. And this is the only way to get it done. So let's look at some more. Borrow some examples from the textbook here. I know there are some sneakier ones. Yeah, let's do this. How about x to 1 natural log of x over x minus 1. If I just plug in, I get the natural log of 1 over 1 minus 1. The natural log of 1 is 0, and 1 minus 1 is 0. So again, I'm like, WTF. But since this is looking like 0 over 0, I can say, okay, by L'Hopital's rule, this is equal to the limit as x goes to 1 of the derivative of the top over the derivative of the bottom. What's the derivative of ln x?
1 over x.
Good. Sorry. And the derivative of the bottom? Sorry, it's a fun morning at the file sticker house. Yeah, 1 minus 0, or just 1. So as x goes to 1, what is this ratio doing now? This is 1 over 1 divided by 1, which is just 1. So in the last example, 0 over 0 came out to -2. In this example, 0 over 0 came out to 1. You see what I mean by saying 0 over 0 is an indeterminate form? It could be anything. Just the symbols 0 divided by 0 aren't enough to tell you what this limit is. I'll show you some more fun examples. This is an example, by the way, where we could not have done algebra to get ourselves out of trouble, right? There's no way to like clean this up or factor anything. The ln x is like, fuck you. How about this one? Lim h to 0 sine h over h. Do you guys remember this limit? This was a pain in the ass to figure out. we needed this limit to prove that the derivative of sine was cosine. And we had to spend like a whole chunk of class, like a good 2/3 of class way back in the day, using a geometric argument to try and show that this limit was 1. Because if you just plug in 0, this looks like sine of 0 over 0, which is 0 over 0. And again, I'm in trouble. But using L'Hopital's rule, I differentiate the top, I differentiate the bottom, and I try again. The derivative of sine h is cos h, the derivative of h is 1. So this is going to be cos of 0 over 1. The cos of 0 is 1. So this is 1 over 1, which is 1. So some limits that in the past were very, very hard, or in the past were straight up impossible for us, are now manageable through L'Hopital's rule. Some more examples. Yeah, okay, those are the ones that they chose too. This is also super useful for limits at infinity. Yeah, let's do this. Only I'm gonna turn it over.
So for this rule, you're just taking the derivative of the top and bottom and plugging in?
Yes.
Okay.
Yeah, so what we do is we first just try plugging in, right? Anytime you're trying to calculate a limit, the first thing you should do is just plug in. If you get 0 over 0 or infinity over infinity, then you can take the derivative of the top and the bottom and try again. And that trying again, the first step there would be to plug in. So yeah, we take the derivative. If the limit looks like 0 over 0 or looks like infinity over infinity, we differentiate the top, differentiate the bottom, and try again. So here's another one, right? We looked at limits as x goes to infinity back in section 2.6. And we had that renormalization trick, but that doesn't always work. Like, what about this guy? As x goes to infinity, here the top is like infinity squared. And the bottom is like e to the infinity. All right, what is infinity squared? If I take a big number and I square it, what do I get?
A really big number.
Yeah, so infinity squared is infinity. What about e to the infinity? If I take a really big number and I raise e to that really big number, what do I get?
And you get infinity.
Yeah, I get an enormous number. So this looks like infinity over infinity. All right, well, this is an indeterminate form. So I'm going to try using L'Hopital's rule. The derivative of the top here is 2x, and the derivative of the bottom here is still e to the x. And now if I try to take this limit, I'll have upstairs 2 times infinity and downstairs still e to the infinity. Well, 2 times infinity, that's also infinity, and e to the infinity, we saw that a second ago, that's infinity as well. So this is still an indeterminate form. So what should I do?
Repeat.
Yeah, one more again. Let's try it again. This is still something that I can use L'Hopital's rule on. So let's apply L'Hopital's rule one more time and see what we get. The derivative of this guy now, the derivative of 2x is just 2, and the derivative of e to the x is still e to the x. And now as I send x to infinity, the top is just 2, and the bottom is e to the infinity. So this is 2 over infinity. What is that?
0.
Very good. This is 0. So in this case, infinity over infinity was 0. If you flip these over, put the e to the x upstairs and the x squared downstairs, things would go very similarly. But at the end, you would get infinity over 2 instead of 2 over infinity, and that would be infinity. So infinity over infinity can be 0, it can be infinity, and it can actually be any number in between. All right, questions on these examples here? L'Hopital's rule is pretty good shit. I'd like to look at something a little more challenging next. Yeah, no, something genuinely more challenging. I guess one more indeterminate ratio is worth looking at. Is there any good stuff in here? I'll get to those differences in powers. All the tangents. No, not really. All right, yeah, let's start jumping to indeterminate products. So it's okay. Yeah, let's do 47. I don't wanna- What if I want to find the limit as x goes to infinity of, how about x squared e to the negative x squared. If I try to plug in infinity here, I'll get infinity squared times e to the negative infinity squared. Infinity squared is infinity, so this is infinity times, and then infinity squared here is infinity, so this is e to the negative infinity. And what's e to the negative infinity? What is this? Who remembers 2.6? It's 0. Yeah, it's 0. The graph of e to the negative x goes to 0 as x goes off to the right. So this looks like infinity times 0. And that's not an indeterminate ratio, but it is an indeterminate form. This is called an indeterminate product. Zero times infinity or infinity times 0, they're fighting each other in the same way that 0 over 0 or infinity over infinity are fighting each other. So this is a problem. But I can't apply L'Hopital's rule right away. L'Hopital's rule says you have to have infinity over infinity or 0 over 0. So can anybody think of a way I could rewrite this expression so that instead of getting infinity times 0, I could get infinity over infinity or 0 over 0?
Do like e to the negative x squared over x to the negative 2.
That would work. So right here, this infinity squared is just infinity. So to go from this step to this step, I'm just saying in both of these pieces, infinity squared is infinity.
Then you get x squared over e to the x squared to the negative.
Yeah, so there's more than one way to do this. And actually, the way I would prefer to do this is the way Robert suggested. So Robert's suggestion was to take this piece here, the e to the negative x squared, and move it downstairs. Because his power is already negative. It kind of makes sense to move him down. So I could say this is x squared divided by e to the x squared, like this. And now as I plug in, I'll get infinity squared over e to the infinity squared, which is infinity over infinity. And now this is an indeterminate ratio, so I can apply L'Hopital's rule. So the derivative of x squared upstairs is 2x. The derivative of e to the x squared is e to the x squared times the derivative of x squared, which is 2x. And we can cancel these. So this is like lim x to infinity 1 over e to the x squared, which is 1 over e to the infinity squared, which is 1 over infinity, which is 0. And this is how we handle indeterminate products in general. So if a lim x to c f of x times g of x looks like 0 times infinity or infinity times 0, then we rewrite, because these are called indeterminate products. They are indeterminate forms. They're indeterminate forms, but they're not the kind of indeterminate forms we can apply L'Hopital's rule. So we need to rewrite the limit as lim x to c f of x divided by 1 over g of x, or lim x to c g of x divided by 1 over f of x. It's up to you. You have a choice. But you got to shove one of the guys downstairs. And the way you do that is by shoving him downstairs as his reciprocal. Chain rule. So the 2x down here is coming from the chain rule. ddx of e to the x squared is e to the x squared times the derivative of x squared, which is e to the x squared times 2x by the chain rule. All right. So the thing we need to take home from this example is if you have a limit of a product, right, one function times another function, and one is going to 0 and the other is going to infinity, either way, then you'll want to shove one of those guys downstairs. You can either shove g of x downstairs as 1 over g of x, or you can shove f of x downstairs as 1 over f of x. That's what we did here. I shoved this thing downstairs as its reciprocal. The reciprocal of e to the negative x squared is e to the positive x squared. Remember that when you see e to the negative x squared, we're always thinking of it like this. Right, that's always what that means. All right, so this is how we handle indeterminate products. There are two other kind of families of indeterminate forms. You've got the indeterminate ratios that we started with, indeterminate products that we just met. The two other sort of families are indeterminate differences, infinity minus infinity, or indeterminate powers. And there's a few different flavors of those. I'm doing on time. I'm going to jump to an indeterminate power. Indeterminate differences are normal algebra tricks. There's nothing really special there. But indeterminate powers are a little bit tough. What if I want to take the limit as x goes to 0 from the right of the expression x to the x? This is kind of weird. It's weird because this looks like the 0 to the 0. And recall that anything raised to the 0 should be 1. But also 0 raised to anything should be 0. So is this 0 because the base is 0? Or is it 1 because the power is 0? Is it something else? This is called an indeterminate power. And there are other ones. So 0 to the 0 is one of them. 1 to the infinity is another one. And I think there's one more. I gotta triple check here. We got 0 to the 0. Oh, infinity to the 0. Yeah. So those are your indeterminate powers. And this is one of them, right? This is 0 to the 0. The idea of an indeterminate form is you've just got two things that are fighting each other, like 0 times infinity. The 0 wants to be small, the infinity wants to be big, so they're fighting each other. 0 over 0. The top wants to make the whole thing small, the bottom wants to make the whole thing big. Here's 0 to the 0. They're fighting each other also. The base wants this thing to be 0, but the power wants this thing to be 1. These are a little bit harder. The way you handle an indeterminate power we take natural log and try to turn the power into a product, and then we turn the product into a ratio. Then we apply L'Hopital's rule. All right. So let me say L is the limit as x goes to 0 plus of x to the x. I'm going to take the natural log on both sides. On the right-hand side, I can pop the limit out of the log. So I get lim x to 0 plus natural log of x to the x. So first you set the thing equal to L. Then you take natural logs on both sides. Then you pop the limit out. This is something you can do with any continuous function. F of lim x to c g of x is the same as lim x to c f of g of x. And specifically, the natural log of lim x to c g of x is the same as the lim as x goes to c of the natural log of g of x. This is true for any continuous function f. And this limits can come in and out of continuous functions. So in particular, they can come in and out of logarithms. So we take the log on both sides, and then we pop the limit out of the log. From here, I'm going to use properties of the logarithm to simplify this piece. Remember how logs work. We talked about this when we talked about logarithmic differentiation. the natural log of a to the b is the same as b times the natural log of a. So I can bring this x, the power of x, down here. So that will get me lim x to 0 plus x times the natural log of x, using rules for logarithms. The rule I'm using here, ln of a to the b is b times the ln of a. Now if I try to plug in, if I send x to 0, I get 0 times the ln of 0. The ln of 0 is negative infinity. This is 0 times negative infinity. So this is an indeterminate product. So we've made it from an indeterminate power to an indeterminate product. So my next step is going to be to rewrite this as an indeterminate ratio, which means I got to shove one of these two things downstairs. And I don't know about you, I would rather differentiate 1 over x than 1 over the natural log of x. So I'm going to shove the x downstairs as a 1 over x. Just algebra. Divide top and bottom by x. Now, as I plug in 0, I get ln of 0 over 1 over 0. The ln of 0 is still negative infinity. And since 0 is going, x is going to 0 from the right, this is like a 0 plus, this is positive infinity. So this is an indeterminate ratio. And now I can apply L'Hopital's rule. So now I'm good, right? We've gone from an indeterminate power to an indeterminate product, from an indeterminate product to an indeterminate ratio. Now I can apply L'Hopital's rule.
How is 1 over 0 infinity?
Picture the graph of 1 over x. We're sending x to 0 from the right. So the thing downstairs here that we're taking the limit of is 1 over x. And if we look at y equals 1 over x and we go towards 0 from the right, we're blowing up to infinity. Or another way to think of it is if you take 1 and you divide by a very, very small positive number, you get a very, very large positive number. The negative infinity, this is coming from, so we've got to know these graphs. Negative infinity here is coming from the natural log of x, right? What does the natural log graph look like? Here's ln x. As x goes to 0 from the right, ln of x dives down to negative infinity. Right, so these are both things that we know from the graphs. We know the graph of 1 over x. As x goes to 0 from the right, 1 over x is going to infinity. And as x goes to 0 from the right, ln of x is going to negative infinity. So these are things that we should know. All right, we come through with where this and this are coming from. Definitely, I don't know what the graph of this whole thing looks like, but I know what the graph of 1 over x looks like, and I know what the graph of ln x looks like. Ln x, as x goes to 0, goes down to negative infinity. It goes way down. And 1 over x, as x goes to 0, he blows up to positive infinity. And we're taking the limit as x goes to 0 from the right, so I'm not worried about this stuff. So now I apply my L'Hopital's rule. The top, ln x, his derivative is 1 over x. And the bottom, 1 over x, his derivative is negative 1 over x squared. And now I can do some algebra. I get 1 over x times negative x squared over 1. which is lim x to 0 plus. You can cancel an x here, and we just get negative x. And as x goes to 0 plus, negative x goes to 0. I'll just plug into that one. So I acknowledge, don't let my tone confuse or upset you, and I apologize if my tone is a little bit dismissive, but this is a complicated chain of things to do. This is not a simple problem. But each individual step should be something that we recognize. So if we need a second to recognize where any of these things are coming from, that's okay, but we should be able to get there. So let's go one step at a time. Are we comfortable with how we pull this x down in front here? Are we comfortable with how we get from here to here? Any questions about the move from here to here? Okay. And then in this line is where we see the negative infinity showing up from the logarithm for the first time. As x goes to 0 from the right, this guy definitely just goes to 0. You can just plug in 0 for x there. The natural log of 0 is negative infinity, right? That's the nicest way I can say that. As you go towards 0 from the right on the natural log function, he dives down to negative infinity. And that takes us from an indeterminate power, what we had before was an indeterminate power, 0 to the 0, to an indeterminate product, 0 times negative infinity. Once we arrive at the indeterminate product, we know more or less what to do. We saw how to handle one of those a minute ago with x squared times e to the negative x squared. I have to shove one of these pieces downstairs. I chose to shove the x downstairs because that'll be easier to differentiate than shoving ln of x downstairs. So I shove this x downstairs, he becomes a 1 over x, and now I've got ln of x over 1 over x, and I try sending x to 0 again. As x goes to 0 from the right, ln of x is still going to negative infinity, and 1 over x is going to positive infinity. So now I've got an infinity over infinity, that's an indeterminate ratio, which means I'm allowed to use L'Hopital's rule. When I differentiate the top, ln of x differentiates to 1 over x, and 1 over x, that's x to the negative 1, has derivative negative 1 x to the negative 2, which is negative 1 over x squared. Now that I've done my L'Hopital's rule, I can try taking the limit again. But before I do that, I realize that this can be cleaned up. 1 over x divided by negative 1 over x squared. Let's just simplify this fraction before I take the limit. Because if I plug in 0 again, I'll get infinity here and infinity here. That's not helpful. But if I flip and multiply the fractions, they simplify a lot. The x's cancel and I just get negative x. And now I can take that limit, that's 0. So yeah, there are several steps to indeterminate powers. If you have an indeterminate power, you take natural logs to turn that into an indeterminate product. Then you verify that the product you get is genuinely indeterminate, right? Like 0 times infinity. And you rewrite it as an indeterminate ratio by shoving one of the functions downstairs. Once you have an indeterminate ratio, you can apply L'Hopital's rule. And once you've applied L'Hopital's rule, that gets you here, you do whatever you need to do to calculate that limit. And this is a limit I could have given you guys way back in chapter 2, because you just have to like do some algebra, flip and multiply, and you get that this is 0. Now that doesn't mean 0 is the answer. What we've seen is that the natural log of L is equal to 0. So L itself, the limit I'm after, I have to solve this for L now. We do that by exponentiating on both sides. You got to remember how to solve logarithm equations. And then the left-hand side, e to the natural log of L is just L, e to the 0 is 1. So the value of this limit is 1. So the limit as x goes to 0 from the right in x to the x is 1. And we can verify this looking at Desmos. There it is. It's a weird function. The base is a variable and the power is a variable. But as you come closer and closer to 0 from the right, the y value is going towards 1. So the limit as x goes to 0 from the right here is 1. And it's easy to change this. If I made this like x to the x squared, or x to the 2x, or x to the 5x, things would change. And you have one problem in your homework that addresses something like this. Where is it? Or you will have one problem in your homework that addresses something like this. This guy, number 60 here, right? All of these are all indeterminate powers. And I'll be giving you at least one or two of these to play with. But that's all we have time for today. I'm going to have to go ahead and wrap things up here because I got to move on to my other class. We'll come back over here in case anybody wants a screen cap. I'll hold at the top of the page for a second. About 5, 4, 3, 2, 1. And then I'll come down here and hold for about 5, 4, 3, 2, 1. Fabrice, I'd like to address the comment in chat there. So it depends on how you approach the study guide. I noticed this too, and it's frustrating from my end as well. I see a lot of study guides with absolutely perfect solutions. And then I see on the tests, if you look, several of those test problems were actually straight from the study guide. And there were a number of people who gave me perfect solutions on the study guide, and then very much not perfect solutions on the test. What this tells me is that we're not really solving the study guide problems ourselves. And that means the study guide isn't going to be helpful. So the study guide, there's nothing wrong with the problems on the study guide. The true-false questions on the test are trickier concept questions. They're meant to be that. That's the point. And if you want to practice those, there are lots of those in the textbook. Come to the chapter reviews for any chapter. You will see plenty of good true-false questions of that nature, many of which are considerably harder than the ones I give you on the test. But the biggest thing that you need to do as you work those study guide problems to make them valuable to you is to work them on your own. Not writing down solutions with other people's help, but working them on your own. And if you get stuck or in trouble, or if you feel like you're not going to be able to get them done on your own to your satisfaction, then you need to come see me in office hours. So I don't want perfect study guides, right? Let me be clear about that. The purpose of the study guide is for you to show me what you can do on your own so I can give you useful feedback for the test. So please don't watch videos or get a lot of help from tutors, or certainly not solutions from other people for the study guide. I'm going to give you full credit for the study guide if you solve all the problems, even if your solutions are incorrect. As long as you make a reasonable attempt on every problem, you're going to get full credit on the study guide. The purpose of the study guide is for me to look at the work that you do on your own as you would do it during the test and tell you what you need to change in order to do well on the test. So don't approach the study guide as problems you need to solve perfectly. Approach them as problems that you are going to show me how you would solve them if they were on the test. So I recognize what you're saying, right? It's possible to have a great study guide and a bad test. But that's not because the study guide is fucked up. That's because we're not really approaching it the way it's meant to be approached. So work the study guide problems independently, at most with one other person, and make sure you don't write anything down that you wouldn't have been able to come up with on your own. If you're stuck, that's fine. Come talk to me, or say that on the study guide. And that way, when I get in there and I make comments on your study guide, they'll actually be useful for the test. It makes me a little bit sad to see really good study guides and then not so good tests. And I totally understand where it's coming from. We feel this pressure when we have an assignment to get everything correct and get it submitted and get the grade, but that's not what the study guides are about. You will get a good grade on the study guide regardless of whether or not the solutions are perfect. But in order to have the study guide be useful, you have to treat the problems the way you would be treating them on the test, meaning not so much outside help. And then also coming by office hours is really, really helpful too, because if you do want outside help on study guide problems, the best place to get it is from me, because I'm the one writing the test and I'll be able to see what you're working on and where you're having trouble, and I'll be able to give you pointers that are useful and relevant to the test. WebAssign can only ask certain kinds of questions. Because it's an online homework thing, there are question types that simply can't be put on there, like sketching a graph by hand isn't something that WebAssign can ask you to do. But it is something that I will be asking you guys to do on the test. So I recognize also that there are limitations to the problem types that can show up on WebAssign. And because we use WebAssign, there's limitations to the problems I can put on the study guide. But make sure you treat the study guide as it's intended to be treated. Solve the problems on your own. Don't worry about having it be perfect. It doesn't need to be perfect. What it does need to be is a representation of your skills. And as long as the study guide is a representation of your skills, I'll be able to give you really useful feedback for the test. So I feel that frustration and I get it. And I don't want to minimize that. You have a good point. But to get the most out of it, just show me what you can do on your own on the study guide. Trust that I will give you a good grade on the study guide, even if the solutions aren't perfect, because that's not what the study guide is about. It's just about giving me an opportunity to give you feedback. All right, I got to run. If you guys do want to talk more, you can come see me in office hours or send a Canvas message. Otherwise, I hope you all have a lovely rest of your day and a nice weekend.